And now I'm going to go to the third part, which is about the phase transition. Okay, so it's only half an hour left, but there are many things that we have already said, so it can actually be rather fast. Okay, so phase transitions. Okay, so here is what you can see in the original paper of Vicsek. These are pictures taken from the paper of Vicsek, and so these are various snapshots of the system that you get from. So it's not very clear, but it's not very clear in the paper already. So you really you need to take a magnifying glass. So basically, this sequence of snapshots corresponds to decreasing noise. So what you get is, for high noise, basically a kind of random motion, and then there are some phases where you have clusters, and in the end you get a full alignment. So as you have is that when your noise decreases, then you get alignment. And remember the videos that I showed yesterday, when you decrease the noise, then all of a sudden you have these clusters that form and that move collectively, right? So that's basically what we see here. And a way to measure this alignment is the order parameter. So again, we already seen this guy, the order parameter with the von Mises. In the case of the discrete dynamics, construct the order parameters exactly the same way. You take the averages of the velocity and take the norm. So essentially, when you get a number between 0 and 1. So it's again this average on the circle. If all your velocities are quasi-aligned, then the order parameter is close to 1. When all the velocities are completely random, then the order parameter is close to 0. Okay, so this is a measure of the degree of alignment. And in the paper by Vicsek, these are the pictures that you can see. So there is one picture where you can see the order parameter as a function of the noise intensity. So you see that for large noise, the order parameter is almost 0, and then you get to some critical value, and then all of a sudden the order parameter increases and reaches 1 when the noise is very small, right? So these are different curves that you get for different numbers of particles in the system. And you see for a large number of particles, you really get a very sharp transition, which is for the physicists, they would call that a second order or continuous phase transition, right? So it's more like of the shape of a square root function, right? And the other thing is that, as I said, instead of looking at the noise, you can use the density. And if you increase the density, and you see also order formation. So for small density, you see an order parameter which is small. And as you increase the density, then you form more and more order, and you get close to 1 for large densities, right? So you have, again, it looks like you have a critical density. Below that critical density, you have 0 noise, and above that critical density, you have some noise. You have no order, and above the critical density, you have order. Then there's been a lot of work triggered by the work by Vicsek, and there was a series of work by somebody from Atomic Energy Commission, Hugues, who has actually shown that you have also phases in some range of parameters of noise or density. You have phases of the system which are strongly spatially inhomogeneous. So you have essentially like traveling waves, traveling bands. So here you have a highly concentrated particles moving in a sea of disordered particles. So here, if you make a cross-section of this picture along this line, and you draw the density, so the density is in black line here, and in the red dashed line, you have the order parameters. You see that you have high density, highly ordered particles here, and around you have low density, disordered particles. So you have traveling bands of high concentration ordered particles, right? So these are, so there's the formation of these things, these bands is not completely understood yet. Okay, there has been some work, but it's not completely. So what I'm going to actually address this today is more like the formation of the homogeneous states. So I'm going to ignore the inhomogeneous states, looking only at space homogeneous system and trying to see how you get from disorder to order in a homogeneous system. And my the study will rely on a slight modification of the model I showed before. So this is the model I showed before, so I can skip the slides rather easily. And then I get to the Fokker-Planck equation for the distribution function. And I'm going, as I said, I'm going to consider only a spatially homogeneous system. So I'm going to drop the space variable, only consider a function of the velocity and time. And here is the collision operator as before. So I still have the noise intensity and the alignment frequency. Here the difference with the previous model is that instead of taking them as a constants, I'm going to assume that they are a function of the, say, local total velocity of the particles. So they are going to be functions of the norm of J, right? So before, we had that these two functions were constants. In fact, in the previous part, we haven't seen any phase transition. We always had a equilibrium, which was a von Mises, and the von Mises is a prototype of an ordered phase. Okay? In order to see the appearance of the phase transition, I need to introduce this dependence. If you take tau is equal to constant and nu is just the linear function of J, then that corresponds to just the model when you do not normalize. You see that you can write the nu times UF as nu divided by J times J. So if nu is proportional to J, this corresponds to the unnormalized model where I just take the projection V perp of J, ignoring the normalization. So this case where I take tau and nu a function of J is, say, just an extension of the case of where I do not normalize this velocity in the model, right? So it's a slightly different model, and we are going to see that this difference allows the emergence of phase transition, which we didn't have before. So in this model, as I remind you that the one is a collision invariant, that means that the total density is constant. So if I integrate this equation with respect to velocity, the integral of q is 0, so I get just that the dt of the integral of f is a constant. So the rho is going to be a parameter in my model. Remember that in the pictures that I showed, we could vary the number of particles or the density. So this constant, which is specified by the initial condition, is going to be one of the, say, bifurcation parameters in my study. Okay, so if I can redo the same computation as before, I'm going to skip the details, and I gain to get as equilibria so a solution of q of f equals 0. I'm going to get the von Mises distributions, right? With this, again, this concentration parameter k, or kappa here, which is going to be equal to this parameter k here in my equation. But now the parameter k is not a constant anymore. It's a function of the j. And that makes a big difference. Okay, because, so again, I have the definition of the order parameter that does not, that doesn't change. But remember that we need, so when we construct the equilibrium, we have a rho times the von Mises distribution, right? And of course, I have to make sure that when I reconstruct the parameters of my model, here is parameters of J, is J, I get the the one that is specified by kappa. Here, so it's sorry, it's a little bit entangled, but the kappa, the concentration parameter, is a function of J, right? So here in this formula, K is a function of J. But on the other hand, J, the current, is the integral of Fv, right? And it's given by this rho times the C1, the order parameter, which is a function of kappa. So on the one hand, I have this, and on the other hand, I have kappa that depends on J. So I have essentially a fixed point equation to satisfy, right? So I have to be sure that my concentration parameter, kappa, is this function k, which I have in my model here, as a function of J, which is rho C1 of kappa. So you see I have this consistency relation, which was trivial before, now leads me to a fixed point equation for the determination of kappa. Okay, and this is actually in the determination of the roots of this equation that I may see different roots, so different kinds of equilibria, so different phases, right? So the consistency relation, so I mean the computation is maybe a little bit entangled, but you have to have in mind you construct an equilibrium. The parameters of this equilibrium have to be compatible with the data in the physical parameter in your system, and that leads to this compatibility relation. And you can actually rewrite this equation a little bit differently. So I will assume, but it's not needed, but it's a simplifying assumption that this function k of j, yeah, maybe I should have precise that this function k is just the ratio of nu over tau, right? So this is, again, like before, the ratio of the competition of alignment to noise, but they depend on the norm of j. So that competition depends on the norm of j, right? So here is basically something that depends on the physics. Let me assume that the physics is such that this is an increasing function of j. So when j increases, k increases, okay? I'm going to assume that this function is increased. It's not needed. It just makes the things much more simple. And so you have an increasing function. You can invert it. So you can actually invert it and take any concentration parameter and look at the current which is associated with it. So this is the inverse function j of kappa of this function. Now if I introduce this function here, I can rewrite this equation as rho is that function j of kappa divided by the order parameter. This is a very simple operation. In terms of physical dimension, it makes sense because j is a current, c1 is a mean velocity, so the current divided by a velocity is a density. So this is basically what this relation says. Another way to see this relation is that c1 of kappa, you see this is the order parameter generated by the von Mises. It's just something that you get from the statistics. Any von Mises distribution will get the c1. So there is no physical content in this. This is just the statistics. On the other hand, this j of kappa is the inverse function of this, and this is where you have put the physics, right? So this relation means that the physics and the statistics must be compatible, right? So it's a kind of a handshake between the physics and the stats, okay? And it has to be rho. So now let's look at this, yeah?
So there's something that is not coming back to me, is the logic. So the equation for the Vicsek model is a natural normalization j over absolute value of j.
Mm-hmm.
You seem to be claiming that you don't have phase transitions for that.
Absolutely.
What you observe, you mean homogeneous, because what you observe numerically is that there are these waves.
Yeah, that's a good point. In fact, what I'm studying is the phase transition of the mean field model, and what I'm observing numerically is the phase transitions of the discrete particle model. So there is a difference here. In fact, when I do normalize and I do the particle simulation, I do get the phase transition. However, when I'm looking at the kinetic equation, I don't get them. That's absolutely correct. However, I do get them at the kinetic level when I introduce this dependence of the parameters on the j. And the phase transitions are very robust. in the particle case, and in the fact that you have to do this little trick to restore them in the mean field model means that the mean field model is a kind of too much averaged in some sense to get the phase transition in the generic case. Yeah?
In this equation, maybe I missed it that you said it. Where is the radius of interaction?
Oh, it's disappeared because we are in the spatially homogeneous case. So here all particles, yeah, because essentially there is no radius. You can have any radius because every point is equivalent. Every point is equivalent because you have a completely invariance by spatial translation in all directions. So you can have any radius of interaction, 0, it's a mean field spatially homogenized model. Yeah. So this is basically the one that you would get in the previous talk when you let the radius of interaction go to 0. So in fact, this study is the seed for generalizing the macroscopic model that I gave before to the case where there are phase transitions. Okay, so this is yeah. So essentially, now you really need to. The only thing you need to do is to. Is to study the roots, the number of roots of this equation. So here, look at what you have. You have an increasing function of kappa here at the numerator, an increasing function of kappa at the denominator. Remember that the order parameter is an increasing function of kappa. So you have a ratio of two increasing functions, and as you know, the ratio of two increasing functions can be anything. It can be increasing, decreasing, can be... So here are different examples of what you could get, right? So these are, different assumptions on the nu and the tau or the k would lead to different curves like that. Let's focus, say, for the time being on, suppose that we are in the case of the blue curve, right? So what I'm plotting here is the function j over c. Don't look at this in the old version of the slide. So this j over c1 of kappa. Okay, suppose it's this curve, right? So what's happening is that now remember that what you need to do is to intersect these curves by a horizontal line, which is going to give you the density. Okay, so this vertical axis is also the density. So you are going to intersect this curve with a horizontal line, and the number of roots is going to give you the number of equilibria. So the one thing that you should have said is that the value kappa equals to 0 is always a solution. Kappa equals 0 means the isotropic solution. So now if you have a density which is, again, let's look at the blue curve, a density which is between 0 and rho star, you intersect with a horizontal line, only solution is kappa equals 0. You only have isotropic equilibria for densities between 0 and rho star. Remember what Vicsek found. No order between 0 and a certain critical density. Then above that density, then you intersect. You have two roots, 0 and a non-zero root. So here you have an isotropic distribution. Here you have a true von Mises distribution with an order parameter, which is the point that lies at the intersection of this curve and the horizontal line, right? Okay? So you have an ordered solution, von Mises, and a disordered one. Which one is the right one? Well, in fact, what's happening is that you can show that the one that corresponds to kappa equals 0 here is unstable, and the one that corresponds to the von Mises is stable. Here in the case where rho is less than rho star, then the homogeneous isotropic solution is stable. And when I'm speaking of stability, I'm not speaking of linear stability. I'm speaking of nonlinear stability. So the fully nonlinear stability. So fully nonlinear stable here, unstable for the isotropic distribution here, stable here. So that's basically what Vicsek has found, because what he has found is that there is a bifurcation when the density is above the critical density rho star.
Stable in the class of homogeneous solutions. Or you
yeah, or spatially homogeneous solution. Yeah. So I'm not speaking of spatially inhomogeneous solution. It's much more complicated. And we do not know. I think Amic has some ideas but so far nothing is really done. So if you look at now a situation where we would have this curve would be the red curve, then what's happening is that you have a unique solution corresponding to the isotropic equilibrium between 0 and that new critical density rho star, which corresponds to the minimum of this curve. Here, the minimum of this curve corresponding also to the intersection with the kappa equals 0, but here the minimum doesn't correspond to kappa equals 0, it corresponds to a non-zero kappa. Then between these two values, you have three solutions, the isotropic one and two von Mises, and above that critical density, only two, the isotropic and the von Mises. So what's happening is that here again, the isotropic solution is stable here from 0 until rho c. That branch of von Mises equilibria is unstable when it's decreasing, and that branch is stable. So you have stable isotropic equilibrium and stable von Mises, stable von Mises. And beyond, it's like before, unstable. Now the isotropic equilibria become unstable beyond rho c, and the von Mises is stable. So here you have what physicists would call a first-order phase transition or discontinuous phase transition, right? So this is basically what we have. This summarizes what I just said, right? So the uniform distribution is always a possible solution, but it's stable only if below this critical density, which corresponds to the intersection of the curve with kappa equals 0, whereas if rho equals larger than rho c, there exists non-isotropic equilibria, and their stability is that the non-isotropic equilibria will be stable if the curve J over C1 is increasing and stable otherwise. And in the case of non-isotropic equilibria, stability means that if you perturb a von Mises, then you will return to a von Mises, but maybe with a different value of the orientation. So it's a kind of an orbital stability rather than a strict stability. And so the tools for this study is that, and this is what really makes the story difficult in the non-spatially homogeneous case. Because we have a free energy in the spatially homogeneous case, but this is not a free energy in the non-spatially homogeneous case. So whatever I'm going to say now is going to go down the drain in the spatially non-homogeneous case, right? So this free energy is this essentially the entropy minus the primitive of the function k of the current of the norm of the J. If you make the computation of the d dt of f, you find this is minus free energy dissipation, which is non-negative. Okay, so this is this expression, which is positive. And so you get that the free energy decays with time, and F is an equilibrium if and only if the free energy dissipation is 0. And so for proving the stability, I'm just flashing in very, very, very sketchy arguments. Essentially, for isotropic equilibria, you're going to use spherical harmonics because you're basically you get a perturbation of the isotropic solution. And you see that actually the behavior is determined only by the first spherical harmonics, which is non-zero, which is precisely J. J is the first spherical harmonics of F. And if you're looking at the time derivative of this, then you get a leading order term, which according to whether your density is larger or smaller than the critical density is going to be either positive or negative. And so this, and the higher order terms are small, so this basically the behavior is controlled by this, and according to the position of rho with respect to rho c, you get stability or instability. And you even get the case of the stable case, a rate of convergence to equilibrium. In the non-isotropic equilibria, you do two things. So first of all, the instability is very, in the case of a decreasing curve, is very easy to prove because you can show that you find in the neighborhood of any unstable equilibrium, you will find somebody that has a lower free energy, right? So if you perturb your equilibrium and you fall here, you will never be able to return to the equilibrium because the free energy is always decreasing. Okay, so if you start from this guy, impossible to return to the equilibrium. You have to go down. So this is how you prove the instability of unstable von Mises equilibria. For the stability, you do two things. The first thing is that you estimate, you perturb your von Mises equilibrium, and you get a solution f of t, and you're constructing a local von Mises equilibrium, which is constructed with an orientation which is that of f. So this is varying in time, like f. And you can see that the distance between f and its local von Mises equilibrium in L2 is estimated by the differences in free energy. And that quantity is decreasing. So it's small computation, and you show that this is true. But the problem is that that doesn't mean that you converge to a von Mises equilibrium. What you could have is that this UF of t could constantly move along the circle and never stop. So you have to show that the UF also converges. And that's actually one big piece of the proof is actually to control that UF, right? But when you do that, when you succeed that, then you also get a rate of convergence of the solution to the equilibrium, and that's given by a certain expression, which involves actually a Poincaré constant for weighted Poincaré inequality, where the weight is this von Mises. So it's a little bit like the gross inequality with Gaussians, right? So you get a spectral gap. So you have a spectral gap estimate here, and so the whole thing is you work out. You rely heavily on the free energy and free energy dissipation to do that. So a little bit like the proofs of De Villette and Villani of the convergence to equilibrium for the Boltzmann equation using the entropy. It's a bit the same kind of method. Yeah, so that's basically the ingredients of this proof. Just a few cases. So, now let me give you examples of both cases of second order and first order phase transitions. I don't remember why I put this. In any case. So the thing is that you can, so the order parameter was constructed as a function of kappa, but in the case where you can actually view it as a function of the density itself, because there is a relation between rho and kappa. And in fact, there is an interesting thing is that if you're looking close to the critical density, you get a formula like this, where beta is less than 1. So remember, you have a shape like a little bit like a square root function. That parameter beta is important for the physicists. It's called the critical exponent. It's believed that you can classify the phase transitions, the second order phase transition, by the exponent gamma. Interesting thing is that you can cook up examples where you get all kinds of beta. Usually in physics you get beta equals 1/2. There are now examples of what they call 1/3 phase transitions, etc. Here you can really cook up examples where you can get all betas between 0 and 1. And this is basically an example of the order parameter as a function of the density for the case of a function k, which is given by this. In fact, the previous case, the one that I did in my the second lecture, corresponds to a limit when epsilon goes to 0. Here you would get just the straight line. So this is why you do not get any phase transition in the previous case, because it's a limit case where you actually send the critical exponent to 0. And you have examples of, you can also cook up example of first order phase transition where the order parameter as a function of rho has this shape, and as usual it gives you, you know, hysteresis curves where you increase the rho, then you jump to the, from the stable isotropic to the stable anisotropic equilibria, and then when you decrease the rho, you jump at a different place. Okay, so you have hysteresis phenomena. Okay, so this is what I wanted to say there. Let me just give a couple of words of what this means for coarse graining. So remember, we did the coarse graining into this self-organized hydrodynamic model. However, the SOH model, the self-organized hydrodynamic model, is only valid in the case where you have von Mises equilibria. What you get in the case where you have isotropic equilibria is more like just a standard nonlinear diffusion. So what you have is when you have phase transitions in the model, you have some regions where you basically are ruled by nonlinear diffusions and some regions where you are ruled by a different model, which is this self-organized hydrodynamics. And somehow you need now to work out the transitions between the two regions, right? And this is completely open. We do not know what kind of transition conditions between regions ruled by a diffusion equation corresponding to isotropic equilibria and regions ruled by SOH model where you have a definite direction of motion, how you should write the transition conditions. Right? So we have some ideas, but nothing really rigorous. So this is in one word what I did here. Let me summarize. So we have here in the complete characterization of phase transitions in the spatially homogeneous case. So we get, so just for the story, there's been a fierce battle between physicists among those who said, okay, it's a first order phase transition in the Vicsek model, or it's a second order phase transition. You know, people have, you know, insulted each other, really. I mean, it's, and so in this case, at least in the spatially homogeneous case, what we show is that we can have either one or the other. So we kind of, you know, reunite everybody. Yeah, and this is basically where I would like to finish. Thank you very much.